Hi, my name is Andreas Reisinger and today we are in the BM lab at the Karl Landsteiner University in Krems and we are conducting experiments on human femoral bone. So let's have a look. Karl. Okay, today we are in a group of 3 people, Dr. Schwarz, Dr. Sönek, Andreas Reisinger, and we are doing tests on real femoral bone of humans. But why are we doing this, Gilbert? So what is the plan for today?
The plan for today is that we're going to test these human femora. These are femora of real human body donor specimen, and they got intramedullary nail implanted during their lifetime because they had a fracture in the pertrochanteric region in between the greater and lesser trochanter. And we want to know how stable these femora are after we remove this nail. So yes.
So this is an answer for clinicians actually.
Yes.
So the nail is removed from the patient and then the question is, will the bone break again or not? Can the patient stand up, walk, run or even jump without suffering from an additional fracture? And we are measuring failure load.
Yes.
Failure load of these specimens. So okay, let's have a look on the specimens in more detail. So what do we see?
This is a left femur from posterior. We can see the femoral head, the greater and lesser trochanter, and when we turn the femur around, we can see the hole of the removed nail.
Okay, and also there is a hole. So what is?
Yeah, this is the distal locking screw to fix the implant.
Okay, and what did you do? So usually down there is the knee, yeah?
Yes.
And you cut off the shaft at some location?
Yeah, actually at the middle of the femur, and then we embedded the femur in a special position. Mm-hmm. And yes, that's what we did.
So what is the special position?
The special position is alignment of 16 degree in lateral and 9 degree in posterior.
And we have 2 embeddings, one at the bottom to grab the shaft, and then there's one hemisphere here at the head, and this is for load introduction, which we will see in a few minutes. Okay, and you put on markers. This is for displacement tracking. So the bone is deforming when it's loaded in the testing machine, and we are tracking the deformation and the movement of these markers in 3D space. Okay, Gilbert, so we mounted now our sample in this metal block.
Yes.
Okay, and the next step?
The next step is we're gonna place it at the Zwick. Then we have to align the femur directly under the machine.
So it's a magnetic laser that is positioned in the center of this disc to align also the sample in the center of the disc. And this looks good. In the meanwhile, okay, this is our Zwick testing machine. It can create up to 30 kilonewtons, and what it's basically doing, it's moving this crosshead up and down, and in this experiment we will compress the head of our sample. And what you see here is a 6-axis load cell. That's a load cell that can measure not only force in that direction, but also in all other directions and all the moments, which makes it to a 6-axis load cell, so 6 different quantities are measured. Okay, in between the load cell and this plate, which is going to exert the force on the head of the sample, there is a bearing. Currently it's not aligned, it should be in the center of this gap, and this allows the lower plate to move to the side, and this is necessary because the bone is deforming and creating a transverse force. And in this case the force is 0 because it can slide. This creates more defined or better defined boundary conditions for the sample. So we can be sure that we have only a force acting in vertical direction on our sample. Okay,
That's good.
fixed and aligned. The metal cap is for a better force transduction. We have a new guest, Victoria Fiedler. She is helping us with the DIC measurement so that I can shoot the movie. We've seen before that there are markers located on the sample. And the reason is we would like to track those markers while the bone is deforming. And we do this with our Aramis system. That's a system consisting of 2 cameras that are filming the sample. The sample is lightened up in blue because that's the frequency these lenses are most sensitive to. And actually what we do during the test is we take a video, nothing else. Yeah? And afterwards this video is processed in a way that the markers are tracked with a DIC algorithm, so a digital image correlation algorithm, and that is capable of tracking those markers and how they are moving in space, quite precisely actually, with I think 20 to 30 microns accuracy. So the noise, so the uncertainty in the position of a marker is around 30 to 40 microns. So there are 2 systems actually connected. One system is the Aramis system and the other system is the testing device. And they have to start in a synchronized manner. So we have a trigger cable that is going here all the way to this controller. And we start, we set the start with a trigger signal. This is the live view of the 2 cameras, and we now are adjusting the center of the screen so that these crosshairs are at the same location for both cameras. Go closer please. Stop. More. More. 3 times. Stop. That's perfect. Okay. That's it. Don't move it. And you see the center of the screen is located or indicated with the laser pointer. So Gilbert is now moving down to get into contact with the sample. So you see the plate is now in contact with the hemisphere, and we apply preload of 100 newtons. You see force set 100. Okay, the trigger is ready.
Okay.
And the test is running. The load protocol consists of few pre-cycles. You see that there are overlapping lines, and then after how many pre-cycles? 10. The load is rising, and now we are already at 1000 newtons. On the y-axis you see the force, and on the x-axis the deflection, and the load capacity was extremely low, only 2000 newtons.
We can see here so-called femoral neck fracture, which is at the femoral neck. And this is actually the biggest fear when you have this kind of complication, because with a femoral neck fracture you have to replace the whole femoral head with a total hip arthroplasty.
Okay, so this fracture pattern is actually realistic.
It's realistic.
Yeah. But at very low loads.
At very low loads, yes. And this is actually the biggest fear we have when we remove these kind of nails.
And today we are testing 5 samples.
4 samples.
4 samples.
Yeah, because this already broke during.
So this broke
embedding.
during embedding, just by handling the bone.
Yes.
It was very weak. Here you see all the holes from the implant. Ooh. Gilbert, what can you say about the samples? So these are very special samples, right?
Yes, they are special samples because these are femora from body donor specimen from the Center of Anatomy in Vienna, and they really had this kind of fracture, this periodontaric fracture during their lifetime, so they got their nail implanted during the lifetime.
Okay, and the nail could grow into the bone, right? Several years.
Yes, for
And
at least
then-
1 year.
For at least 1 year. That
Yeah.
was the criterion.
Yes,
Okay.
and we checked with X-ray and CT scans that this fracture was actually healed.
And you extracted then the nail to
Yes, we extract the
create
nail.
those samples we have here. And this is a very special sample. So what happened here?
Yes, that's a pretty interesting sample because we can see a so-called heterotopic ossification, which sometimes happen because the bone marrow comes out of the bone, and then the ossification starts sometimes, and then it looks like this.
So this is all bone. This is not
Most of it is
Yeah,
is
there's
bone. This
some
is all
soft tissue,
bone.
but-
There's a little bit, but most of it is bone. Yes.
Okay, very interesting. And could this person walk, do you think, or is
yes.
it rather stiff?
No, I think this doesn't bother the patient at all. As long as it's not here next to the greater trochanter, it shouldn't bother the patient.
Okay. And this is our last sample for
This is our last sample, yes.
today. Kamera läuft. Kamera läuft.
Okay, start.
Okay, broken.
Was ist gut?
The maximum force was 1,700 newtons. So very, very low for a human femur. The test series is finished. We tested these 4 bones today and measured the fracture load for stance load case, and this bone already fractured during the preparation. So these are very weak samples after extraction of the nail, and we will have a look on the results.
We see here at the beginning the pre-cycles. We did 10 pre-cycles at the beginning, and then we did the loading until the peak, and the peak is actually the fracture of the bone. And as we can see here, the maximum load was 2000 Newton.
But this seems to be very low. So what does
it's
this
very low.
mean clinically?
It means that when we remove the nail, patients should not be allowed to weight bear at all after the removal.
So this does mean that the patient that has a nail extraction cannot walk, actually, cannot load the bone.
At least, as we say right now, 4 weeks, no single leg stand. Yes.
So does it make sense at all to remove the nail then? So, or
Well,
should
in
it stay
some-
inside?
I would say in younger patients you should keep it. and only when you have severe complications then to remove it, because the maximum load is really low.
So what are the usual maximum loads for this load case? So when you have a healthy bone? So from my experience, it's around 10,000 newtons. So 5 times as much when you are healthy. Yeah. So 4 to 5 times as much.
Yes.
All the samples we have seen today in the testing machine have been scanned by Gilbert in a computer tomography system at the hospital.
Yeah, exactly. And they were not only scanned once, but they were actually scanned several times. So once before the nail was extracted, and then after the nail was extracted, and even after the sample was cut and embedded. And now we can actually have a look at these scans on the computer. So what you can see here are these 3 scans. And on the leftmost side we have the scan that was taken before the nail was extracted. Now it looks like the bone is intact and you cannot see really the nail, but we can actually make the bone a little bit more transparent, and now you can see how there is the nail still in place here in green, right? And now in this second scan in the middle, what you can see is that there is actually no nail inside anymore.
Because Gilbert took it out.
Yeah, because Gilbert took it out and took a scan afterwards again. And then we have the final, the prepared specimen, where you can see it was cut. And you can also see the embedding at the distal end and at the proximal end. So this is good to have, but it's also very interesting not only to see it from the outside, but also to have a look now inside the bone, because that's what we can do with a tomographic method, right? So now we can have a look inside the bone structure.
So this is after extraction, so the nail is gone here and we have cavities.
Exactly, yeah. So, and it's also you can also see the embedding here. Yeah. Okay, so this is a scan of the very specimen that we tested, and you can see there is actually a huge bone defect. Yeah. And what is also very interesting to see is how the bone adapted to the removed nail. So for instance, you can see here more bone on the proximal side, but there is really not a lot of bone left above the nail, right?
And this was the location where we saw the fractures today. So I think half of the samples fractured there. Some of them were just pressed together, so the neck was pressed into the head, but 2 had a clear fracture here.
Yeah.
And the reason could be that the bone lost a lot of its mass, a lot of its material at the top here. Okay, that was it. I hope you found it interesting. Have fun with mechanical testing. Bye.
Goodbye.
Bye.
Bye-bye.